Alright, welcome to this third video on vectors. This one is going to be a little bit of an introduction on adding and subtracting vectors. And the first thing that I wanted to say here is that the most sort of basic and first type of adding that you see for vectors would be something like this, where maybe I'm going to add vector A and vector B. Remember to underline them always. And it works like this: 3i plus 4j, and we're going to add to that vector B, which is 5i minus 1j. You don't write the 1, you just have minus j. When you add these, they add very much as logic would dictate, and so I have 3 i's and 5 i's. You can think of them as coefficients 3 and 5 of the same variable I. Slightly different, but you can think of them like that. And so I end up with 8i plus 4, and then minus, it's plus minus. So in a way you can think of these as having brackets, because if that was a minus and this was a minus 2, then obviously you would add there. So here you have plus 4 minus 1 plus 3j. And that is how you add two vectors algebraically like that. Now remember that I said in my previous videos there was a faster way of writing vectors, and hopefully you'll see the value of that if we do it right now. If instead of using normal vectors we use column vectors, we have this. Sorry, I copied the wrong. 5 minus 1. That's it. 8 and 3. And so that was way quicker than that. Hopefully you can see that. And for subtracting, you do the same thing. So adding and subtracting vectors in this way is super easy. In 3D, it's the same stuff, but in three dimensions, you could have two vectors that look like this. 3i plus 4j was the first one, plus 5i minus j. Oh, sorry, getting carried away here. It needs a third dimension, so plus 2k, for example. The k needs to be underlined, and so does the I. Going too fast. Plus b, and b is going to be like the second, let me take this one and modify it, so 5i minus j plus k. And just for the sake of argument here, if there was no k, this could still be a three-dimensional vector, right? But with a zero component for k. So if there was no k at all, you would write this vector here as 5 minus 1 and 0. If you knew that it was a 3D vector, because here this one is 3D. So if you're going to be adding two vectors together, they're always going to have the same dimensions of either 3 or 2, or in some cases even more. Bueno. So keeping this like this, then that would be, 3 plus 5, 8, 4 minus 1, 3, 2 plus 1, 3. So that would be, writing it all out, 8i plus 3j plus 3k. But if you do it in column, you just do 3, 4, 2, 5 minus 1, 0. Sorry, not 0. We said in the end that this was going to be 1. Equals 8. 4 minus 1 is 3. And 2 minus 1 is, 2 plus 1 is 3. Okay, and here the notation you need to include plus to know that you're adding those two vectors together. So I jumped that. Sorry, I'm going a bit quickly. Okay, so that is how you add two vectors in 2 dimensions or in 3 dimensions. Super easy. And also how to subtract them. Same thing. Now, what are the requirements for vectors that you're going to have to know as we go deeply into the topic and it starts to get more complicated? Well, you need to have very much in your head Pythagoras theorem. So that's easy peasy. You need to remember your cosine rule. So remember that. Just a quick refresher here. A squared equals b squared plus c squared, which looks exactly like this fellow over there. There's a reason for that. And then minus 2bc cos of the angle A. And remember that A and B have to be labeled in opposite sides of the triangle. So if this is my triangle, let me not be lazy here. Let me do things properly. If this is my triangle, remember that the cosine rule is used when it's not a right angle triangle, because otherwise you just use Okatoa, right? So if it's not a right angle triangle, hopefully it doesn't look like one to you, then you label the using the wrong tool. You label the sides in opposite ways, right? If this is A, this is side A. And if this is angle B, if this is angle A, this is angle B, and this is angle C, then this is side A, this is side B, and this is side C, right? Remember to label it properly like that in opposites. And if you do that, then this is the cosine rule. So if you need to find an angle instead of a side, you just jiggle this around and leave it in terms of cos A. That was the cosine rule. And then trigonometry, normal trigonometry, which comes out of the acronym that hopefully you all remember, SOHCAHTOA. Okay, you need to know these to be able to do vectors and have a bit of imagination and visualization. Okay, now let's see, just run out of paper. Let's see geometrically what adding two vectors means. So if I have, let me do first of all the easiest case here. If I have a vector that looks like this, and another one that looks like this, and I add them, I hope you're asking yourself right now, well, you're telling yourself that that's not vectors. For them to be vectors, you need to know which way they're adding. And this one could totally be in that direction, but we'll do that at some other point. Let's imagine that they're both acting in those directions. And those are the two vectors that I'm going to add. And here I'm going to do another different example where, let's see, the vectors are going to be one of them like this, and the other one like that. And let's see the difference between these. Well, here's where geometry starts to play a part, because and the thing that I said in the very first video out of the three starts to also to play a part. If I am going to add these two vectors, the key here geometrically is to think of it as in terms of adding them head to tails. Head to tail. So that I need to move this, one of the two vectors, in this case I'm going to move this one, such a way that the tail of the vector, which is over here, that's the tail and that's the head, moves to the head of the other. So the tail of this vector here needs to move to the head of the other. In other words, I need to come here to the head of the other and say I'm going to move, but keeping the direction the same. Remember, vectors never change the direction of themselves. The way they act is the way they act as part of their properties. This one acts up, so wherever I put it, it's going to act up. So you can think of gravity, for example, as a vector that always acts towards the center of the Earth, right? If this is the center, wrong tool again. If this is the Earth, then the vector is always going to point towards the center of the Earth. Now, well, that example is actually slightly different, because depending on where you are, that's going to change, right? But if you imagine a model where the floor is a little bit zoomed in and this is flat, then the vector for gravity is always kind of pointing down into the floor and perpendicular. Yeah, but if the Earth starts then rounding, then it stops being a perfect vector because it always points towards the center, but it's not the direction is not kept in that coordinate. It would be kept in a spherical coordinate. Anyway, forget that for now. It's for later discussion. But here you have now what you have to do. It's very simple. You just say, well, once I've added geometrically my two vectors, which is what I've done there, what remains to be done now is to say, well, from the tail of the first vector, I need to get myself, sorry for the sound, phone. From the tail of the first vector, I need to get myself to the head of the second one. So here's the tail of the first one. I need to get myself to the head of the second one. And that is what we call the resultant vector. We normally call it R, and it's the result of the sum of those two independent vectors. So let's call this one A, and let's call the other one B. If I shift one to the other side and then I add these two, well, you can see that assuming that this was already 90 degrees, this is also going to be 90 degrees over here, right? And it's very easy to add these two. You can just do it with Pythagoras, and that's why we said in the previous one that you had to remember some Pythagoras to be able to do these problems. Now, the way that you add these really to get the size of R is you would say this. You would say that the magnitude, hopefully you can remember the symbol for the magnitude of things, right? Magnitude of x, modulus of x. This is similar to the modulus. Magnitude of R equals the magnitude of A squared, this should also be squared, plus the magnitude of B squared. And that's how you find your answers. If you really want to know how long the vector R is, you take the square root of both sides and you say that R is equal to the magnitude of A plus the magnitude of B squared, all square rooted, and you get R. Right? If I write A and B without lines, it's also kind of saying the magnitude. It's a kind of a faster way of writing all of this. So that's to find the magnitude of R. But I remember that a vector needs both sides, so it needs both the answer of this, which is going to be the length of it, how big it is. If this was forces, that would be the equivalent of whatever. The answer is 7, then that would be 7 newtons of force. But that's not a vector if it's just 7 newtons. You need to also know what direction. And that, for directions, we need our angles. So this guy here would be the one to find in this case, and so you would have to do SOHCAHTOA. You have the opposite and the adjacent, right? This is the opposite and the adjacent. So we're talking about tan. So here you would do tan theta is equal to the size of B divided by the size of A. And then to find theta, you would do tan to the minus 1 of B over A. Easy. Hopefully you can remember all of that. You get your angle for theta, and then you would have your answer. For example, the answer was 8 newtons. You would say 8 newtons to, I don't know how many degrees, if that was 20 degrees north of east, for example. Or if this was defined as east and this was defined as north, then you would say you could say 8 newtons north of east. That would be enough. Sorry. 8 newtons north of east. Newtons north of east. Okay? Or you could say 20 degree, sorry, I messed up there. 8 newtons, 20 degrees north of east. Or you could say 8 newtons, 8 newtons, you could say 8 newtons, 20 degrees anti-clockwise from the x-axis, if that was how it was defined. or things like that. You would basically have to define it, or you just make a diagram and you just say 20 degrees, and you just say as in diagram 8 newtons with the direction as in the diagram. So here you would just say 8 newtons. That would all work. And yeah, the one that I'm least happy with, it's kind of a bit of a fudge, I'm sorry about that. The one that wouldn't work very well would be this last one there. Doesn't really, anti-clockwise of the x-axis, not very clear. But you could totally write this 8 newtons 20 degrees north of east, or you could just do it in the diagram. You could indicate in the diagram, see 8 newtons direction as shown in the diagram, and you show it here with the 20 degrees. Okay, what about this one over here? Well, I am kind of running out of time, so I'm going to leave that until the next video. But just to give you a quick sense, because these angles are not at 90 degrees, you're going to have to add this vector over here, like so. And your resultant, hopefully you can see, is not going to end up being a simple Pythagoras theorem, because here you don't have 90 degrees. So, if they don't tell you this angle, if they just tell you that this is 7 newtons and that's 8 newtons, for example, or 7, any kind of unit, then you can't solve the answer essentially, because you're missing one piece of information, right? The cosine rule, you need 3 things, and you need also 3 things for the sine rule. So here, b and c minus 2bc cos a. So here you would need the angle. The 3 things that you're being asked to have are these 3. And if you don't have the 3 of them, you can't work out the size of the third side. Similarly, if you wanted to work out this angle, you would need the 3 sides. Hopefully you can remember that from cosine rule. And similarly with the sine rule, you also need 3 sides out of the, well, three pieces of information out of the whole triangle. But we'll do that later on because we run out of time. You see that adding them in this form is very easy, and in this one you need a bit more info, but it's still essentially cosine rule, sine rule, etc. Alright, see you in the next video.